Thank you. And we're going to welcome Ashok Singal. You're going to sit or?
I'll sit. But can you stick it here?
Yes, sir.
Yeah. Okay. I think this is sufficient. Yeah. Some people wonder why this chair. Like yesterday, Arunima told me, can you chair this session, 2 to 4? I said, I'm myself going to give talk, but any case, you put the chair, so I'll sit on that. Any case, so actually, I got fever yesterday. Maybe it was a bit cold there at dinner time. So I asked her to put chair so that I can sit meanwhile. Okay. See, anyhow, my name is Ashok Singal, if you don't know. And I am actually a radio astronomer. I was working in UT, then GMRT. And then I used to work on AGNs, radio galaxies, quasars, their physics, radiation processes, and also a bit of cosmology, like cosmic evolution of their sizes and luminosity. But then I got interested in this, which my friend Pajwal told me that I must tell the story. There is a slight, some few minutes story behind it. It all started with a movie called Deep Impact. Some of you might have seen a Hollywood movie where some comet or asteroid is on the collision course with Earth, and they think all life will get wiped out. Not bad, maybe. But in any case, they send some scientists, astronauts. They take some nuclear devices, and idea is to shatter that thing. Whether you people die, it doesn't matter. But to shatter that asteroid so that it becomes smaller pieces, and hopefully it will go away, not coming directly.
There's Bruce Willis, right?
Pardon?
Bruce Willis, was that movie?
I didn't follow. Okay.
Oh, the other one.
Yeah. Any case, so in that they had sent some spaceship with some 5-6 persons. And of course, in movies they make a lot of sound and sights show. A lot of sound, although sound should not be there outside. And a lot of stars passing by and all that through the windows. And then I had taken my children to see this movie. Okay, my daughter, she was school-going age, and son was even smaller. He was also in school. Then my daughter asked me, Papa, can we ever go on a space voyage like this? Now, I come from PRL, Physical Research Laboratory, which is part of Department of Space. But I said, in spite of that, neither I can go to space, nor I can take you. But maybe I can take you to a space voyage. So what we did, I took a mat, what we Hindi call chatai, yoga mat or something, and went to terrace, spread it, and we lie down with children around me. I said, look at the stars. And they looked, they said, okay, what is so great? I said, we are actually moving around the sun, forgetting other things, at 30 kilometers per second. So we are having a space voyage in that sense. In fact, most of these spaceship will be going 7 to 10, 11 kilometers per second, but we are having faster speed. But they just thought I am pulling a faster one. So they were not amused. They said nothing is moving. And they went downstairs. But I was still lying down, and then I was wondering how to prove that we are moving. That we hear that we are moving, but how to know? Because motion is so small, angular motion is almost zero. And then I started wondering, and then I thought, okay, there is a aberration is there, plus Doppler effect is there. Can we use that to detect our motion? And then, of course, I knew that CMB has shown that we are moving at some 370 kilometers per second. So can we do same thing using some radio sources? Stars are too near, they are part of a galaxy, nothing. But I knew there was a NVSS catalog of sources, 1.6 million, 1.8 million sources. So can we using this Doppler effect and aberration, and can we find some sky brightness due to radio sources, which is brighter in one side and fainter other side? That will, and I expect a similar motion we'll get as for the CMB. And that's how I started in this game. Then, of course, I downloaded the data. And I was new to this game, took longer, and to learn everything from scratch. But it was not difficult. Physics was not difficult. And then it took me 6 to 8 months to find the first results. And they were a bit surprising. Because although the direction of motion turned out to be same as CMB, within errors, of course, within 1 to 2 sigma, but the amplitude turned out to be 4 times. That was 370 kilometer per second. What I got was 1500 to 1600 kilometer per second. So that was a bit surprising. I thought something is wrong. Of course, the CMB thing can't be wrong. I mean, so many people have worked on it and so famous. So, but then I kept the thing aside. And in fact, I sent it for publication 5 years later only. This happened 2006. I sent it for publication 2011. In between, every few months, I'll pick the thing again, try to run it. I learned different languages. There's IDL, interactive digital language. Then MATLAB I learned. And I tried many ways. And whatever I do, results were coming same. So I was sure that nothing wrong in my results. Well, if they are wrong, but what I am deriving is correct from the data. And then 2011, I sent for, and what I did was I looked at radio brightness of the sky. I take the all integrated sources and their flux and multiply with that and get the brightness. Any case, and as they say, ignorance is bliss. I didn't know that already 2 groups have worked on this. I forget the names. I noted one was, of course,
Blake and Wall. Chris Blake and Jasper Wall.
Yeah, Blake and Wall. Otherwise, Blaise et al. And both, although they had actually got some results that they had got higher than the CMB, but they concluded that this is all due to our signal to noise problem. And they said that our results are in concordance, or whatever the word. We are matching with the CMB results. All right, I didn't know. If I knew that they have done, I would not have proceeded, because then I thought everything is done. Any case, of course, once you want to send the paper, then you have to do literature search and all. Then I found these papers. And also I found 2009, there's a paper by, I forget the names, Crawford. Crawford had done the NVSS analysis theoretically, and he had come to conclusion that this catalog is not big enough to, so we can't detect a motion more than 1 sigma level if it is CMB. I didn't know, otherwise I would have gone up, okay, because I was doing just out of curiosity. Any case, so once the results came, I sent to one famous journal, I won't name that journal. And then the editor, he or she must have consulted some referee also. And they came to conclusion that, no, it must be all wrong, because these are all famous results, so many people have worked, well known. They said, no, we won't take your paper. And then I sent to FJ letters, and there it got accepted immediately. So I may, meanwhile, sometimes sit here because of my fever, but okay. So, is it on? Maybe it's off. I think he has switched on. देखो on है? Oh, am I sending for wrong direction? Yeah. Anyhow, we start with cosmological principle, everybody knows, but I still, for sake of completeness, I listed here. The universe to a co-moving observer should appear isotropic without any preferred directions. And of course, if we have peculiar motion of the solar system, let's say, and we are part of it, observers, then we may see some properties of the cosmos. Observed properties may show some dipole asymmetry. And of course, such a dipole asymmetry has been seen CMB, from which the velocity of 370 km per second has been inferred. Certain direction. This, of course, is the famous diagram everybody would have seen. Okay, now, from cosmological principle plus some observations, we know that there is no relative motion between various constituents of the universe. Let's say redshift 0.05 or 0.1. Only beyond that. Beyond that, there is nothing. Below that, of course, there is a, what we won't call it peculiar motion, it is just objects moving with respect to each other. Now, and we may call these constituents at redshift, let's say 0.1, as co-moving coordinates. These may define co-moving coordinates. And if you have motion with respect to that, now your motion may be, of course, motion of Earth around Sun is not important, which is 30 km per second, which in any case gets averaged out over a year. But Sun motion around our Milky Way, something like 230 to 250 km per second, plus motion of our Milky Way with respect to other local group of galaxies, that with respect to Virgo supercluster, plus other at whatever larger scale. So adding all those vectorially, we get what we call our peculiar motion. So now, this is what I already mentioned, that if we are moving, then aberration and Doppler effect will make the sky brighter that side. You can work it out, but of course, that has been done by, I forget the name. What's the name of two people? No, who? Who worked out the formula? Total, not aberration. Alice Baldwin, yeah. I'm bad at names. Okay. So, of course, initially I didn't know that, so I tried to work it out myself, which in a way it's helpful also. You understand it better. But then finally I had to go to that. Any case, so that shows in some direction, of course, they have worked out number counts, but the sky brightness is not very different from that. You just integrate your source emission from that direction you take. Then one certain direction, depending upon the speed of the observer, okay, you will see the sky is brighter, other side it will be fainter, and there will be cos theta effect. Of course, change for every source is tiny bit. So, but when you take integrated, it will be sufficient. It's like everybody gives 1 rupee to me, I'll be millionaire there if millions of people give me, but otherwise for 1% it will be nothing. Okay, so when after 6-8 months struggle, when I got the first results, then I found that the speed of Earth's movement seems to be 1500 km per second, while CMB was saying 370, although direction turned out to be roughly same. So that was a paper I had published here in 2011. And in fact, in that I think it was the first time I mentioned that such a genuine difference between two dipoles, which implies an anisotropic universe, and which may be changing with epoch perhaps, and which will be violating the cosmological principle, and then in any case on which whole modern cosmology is based upon. This is actually radio brightness, sky brightness, radio sky brightness. Then I made a contour map, and which that near 3.8 there is a plus sign, though I have marked this way plus, actually plus sign, which is the best value I found for the dipole direction. and that circle with a dot inside, that's the CMB dipole position, which are not very far. It's slightly more than 1 sigma, but less than 2 sigma. But the amplitude, now these amplitudes what I have given to 3.8 and all that, they are in terms of CMB motion. So I could directly compare. Instead of giving 1500 kilometer per second or so, I give him in terms of 370 kilometers per second. That's my unit. So 3.8 or 4 means that's 4 times the CMB value. Okay. Now, this same thing, words, that although the solar motion appeared to be about 4 times the CMB value, the direction, however, turned out to be within errors to be in agreement, within 1.5 sigma or so. Okay, afterwards, okay, at that time, of course, there was a lot of, I won't say a lot of criticism, mostly people ignored it. I mean, they'll only if they'll criticize if they believe or they think it's important. But there was some, wherever I gave a talk or met some people, they used the word which I forget again. Okay, yeah, there was a lot of skepticism, I should say. That's the word I was looking for. So there was some criticism, but any case. But then more than half a dozen groups, starting from Germany and IIT Kanpur and these people, and they also found that the not only NVSS catalog, but some other catalog also, they are showing the dipole amplitude, which may be anything 2, 3, 5 times. In fact, we had even TGSS map, which TG, Tata Institute, T stands for that, GMRT. So TFR GMRT also has a survey made of the most of sky. I used that also. In fact, that gave 10 times this. I don't know. I'm still not able to resolve that. But in any case, the motion was coming much higher than the CMB. And direction in all of these cases, even whether 2 or 10, the direction was turning out to be almost similar as the CMB, within 1 to 2 sigma. So that goes against CP, cosmological principle. Okay, one thing is either you can say that all this has nothing to do with solar peculiar motion, it is something else. But that means there is some intrinsic anisotropy, including in CMB, okay? And also in radio sources and later infrared sources and others. Now that is even worse. That means it's nothing to do with our motion, which is related to us only, but it is property of the cosmos, which is not isotropic, which goes against the cosmological principle. All right, so this was the old story. Okay, Sebastian yesterday, 3 days back, has summarized most of, yes, you want to? Yeah.
Basic question. So why AGN specifically and any type of AGN? Because as I understand, AGN show a lot of diversity. Maybe you'll mention this later.
Oh, you mean why all different types of AGNs are showing?
No, which AGNs did you choose, or is it just all kinds of AGNs?
These are all type of, these were radio sources,
Okay.
which we believe that they are at high redshift, redshift 1 to 3. Okay, NVSS catalog is radio sources. And then there are infrared sources, which are again believed to be quasars. Of course, I'll say believed to be. I mean, nobody has actually done redshifts and all that, but statistically you can see, okay, whatever type of sources, unless they happen to be within our galaxy and something is changing their properties, their directions, which also will be strange. But whatever type of AGNs far off are there, okay, and when you have one class of AGNs, one class of AGNs, each class itself is showing that the direction is same way CMB, they are showing dipole, and direction of that dipole similar to be CMB, but the amplitude turns out to be 3 to 4 times higher. Okay, all right. Now, recently, about a year back, okay, 10 minutes. Next up speaker is not there, but I don't want to take that person's time. Okay. So then I got interested in this problem about a year back, that there's a catalog of, I don't know how to pronounce, QUIAIA, something, Qua something. Qua something, okay. Okay, so whatever I speak, you take it that I'm speaking that. It has come from Gaia data, basically. And that has 1.3 million quasars, and they claim their spectroscopic redshifts and positions are there in sky. So I took that, and I thought, okay, redshifts are indicator of motion. So instead of number densities or sky brightness, why don't I look at redshift? See, if some source is going this way, you look this way, quasars are going away. And if you are also moving this direction, you are sort of chasing them. So the redshift will be lower, but opposite direction, redshift will be slightly higher. And there will be cos theta effect. So then this is that. Okay, this my paper is just published about a month back. Okay. Okay. Now, cosmological principle, you expect redshifts in all directions statistically will be similar. Okay. In fact, almost all our cosmology, where we start with Hubble diagram and all that, that doesn't depend upon direction. We take all the objects with their magnitudes and redshifts and plot it. Okay. Now, if you have a, let's say Z0 is a cosmological redshift, and V is the velocity of our peculiar motion, solar system or observer, let me say, and that object is at angle theta with respect to your direction of motion, then the observed redshift will be this, 1 plus z into 1 plus z0 into 1 minus beta cos theta. Beta is, of course, velocity in units of c. So you can see that over the, okay, I can go to next. The observed redshifts will be related to intrinsic redshift, cosmological redshift, or what I call, with a d cos theta effect, where cos theta is direction, and d is the dipole magnitude, which you will get. And so now what you do, what I did was, I divided the sky into 10 by 10 bins. There are about 422 cells. And taking center of each of these as expected direction of motion, I take 1.3 million quasars and make a least square feet of a straight line to x, which is cos theta, into z. Okay. Now, if there is a genuine cos theta effect is there, you should be able to get from this d and z0, which is average z0. Now, of course, you may not be moving that direction which you are taking. So I try all directions in sky, all 422 directions. So this is how I divide the sky into 10 by 10 degree cells. And when now I plot all those 422 points, they should show cos theta behavior. But when I take pole direction same as the CMB pole, then I don't get any cos theta effect, hardly anything. It's all scatter diagram. However, if I take the best out of all these, I get this. There it fits the cos theta, and the direction turns out to be 279 right association. Okay, I'm giving it degrees right association, and minus 29 other declination. Okay, I can do some 3D cos theta fit to this, to chi-square fit, and try to see which direction gives you best. That's how I got that 279 minus 29. Now this is a contour plot. Radio astronomers are familiar with contour plots, but others also. In fact, first I made just contour plots, but then the editor or referee asked me, why don't you make it a heat map? So colored heat map. So that's what I made. And this red one, oh, yeah, yeah, this one. This is the best, what I call optimum direction, turns out by chi-square fit cos theta, and these are contours, and maximum value turns out to be here somewhere 4, okay, 4.5 something, and minimum direction. See, if velocity is minimum, that means redshift is high. I have not plotted redshift, I have just plotted the velocity, but they are just can be translated into each other very easily. And this is right extension definition. Okay. Now, when I got this result, just I got curious due to some reason. Okay. So I put the galactic plane, the dotted line, thick dotted line, galactic plane. So I was surprised that this thing came right on the galactic plane, that cross thing. And then I plot a galactic center, which is that this one. A galactic center came right there. So that was even more surprising. Why it has to do anything with the galactic center? I'm using quasars. Okay, it should not have anything to do with galactic center. I'm taking the peculiar motion of sun. Of course, unless you say the sun is falling towards galactic center, which we know it's not. At least all previous observations shown it has 250 km tangential motion. But anyhow, this is the data which showed. Then I got worried also, that I spent a lot of time checking my program, and I did 1,000 simulations. And this is out of those simulations, one of that I am showing, where I chose, see, I randomized all the redshifts among the known sources, about 1.3 million quasars. I took the same position, but randomized the redshifts, scrambled it. And then over that I superimposed a motion. Okay, when I take randomized thing, when I run my program, I don't see any dipole. Then I superimpose upon that dipole, which is, in this diagram, it's towards galactic center of amplitude 5, but I tried all sort of things. And I almost always got the correct, whatever was input, similar I got the output. So here you can see this diagram is showing almost similar thing as shown from the actual data. Yeah. Okay. While this one is from the simulated data. Anyhow, I did 1,000 simulations, and this is all right ascension definition. No information about galaxy coordinates has gone into this. So it should not have anything to do with galactic center, otherwise, except, of course, later I drew that galactic plane and I put the position of galactic center here. Okay, but still I was worried. I expected it to give you me the same thing as CMB, but it didn't show. Okay, then I, instead of 10 by 10, 422 bins in sky, I made 2 degree by 2 degree, 10,000 or so bins in sky. Then I tried the old one as well as new, and they didn't show any. I mean, the 10 degree was as much good as 2 by 2 degree. Okay, so this I just showed ki so many bins I had made. And then what I did, the sample, I broke into 2 parts. One is fainter, which is greater than 20 magnitude, and brighter, which is less than 20 magnitude. Then this one is, these are brighter quasars, less than 20 magnitude. G is for Gaia magnitude, okay? And also, these are for fainter quasars, greater than 20 magnitude. Okay, here I have plotted in galactic coordinates, just to, so that one quickly can see. And you can see everything is coming close to galactic center. Although initial what I did started with right ascension definition, so that nothing about galaxy information goes in. All right. Then I did this table, which there were too many entries, perhaps 20. Then till now I use all the sources, which include even in galactic plane. Now I started dividing them galactic plane 10 degree, 20 degree, 30 degree. And you can see the results are not very much different. P is coming 4.6, 4.9, 3.8, plus minus error of course. And direction also not very away from galactic center, okay, which is now in galactic coordinates. In fact, I did was that I took all sources greater than 30 degree in galactic plane and all sources less than 30 degree, that is right in the galactic plane. They also didn't really show any spectacular differences and all that. Okay, of course, these are all quasars with no redshift. They may lie in galactic plane, but they are still quasars. Then, of course, brighter sources also similar thing I did. Then fainter sources, then even more brighter sources I went. In fact, I even did that in the declination, I divided the whole thing plus minus 30 degree. And both of them showed quite similar results. I mean, it was not going much away from the galactic center, the dipole. Of course, errors increased as I have sample was reduced. All right. So this is my result. I have not much interpretation. I tried to think over a year. I didn't get any solution that why it happening. So I just listed out many things. What can be the implications? Okay, of course, one way is that, okay, one may say you ignore it. Something may be wrong with the program. Okay, that should be the attitude, fine. I myself will have the same attitude if somebody else has presented the same results. But as I said, by doing the simulation, 1,000 simulation, 500 of them I did in galactic coordinate, 5 of them I did in rectangular coordinates, alpha, delta. And they all gave the results what you expect from the input. So I don't think anything is wrong in the program or analysis. And then maybe some quasar with anomalous redshifts are there, which are pushing your dipole direction toward the galactic center. But then if the sample may have a bias, but then of course that is taken from Gaia data, both redshifts as well as the positions, but then that will start raising question about the Gaia data itself, which unlikely. I don't know, maybe nature of quasars we have to start rethinking, like Jain, Narlikar, Burbidge, Arp, and Hoyle in 60s and 70s. They never believed quasars are at high redshift. They thought they are part of either our galaxy or nearby. That thing. Or do we have to start worrying about Milky Way, like we think the sun is going around, but here by using quasar we found the direction of sun's motion. And if it is toward galactic center, are we somewhere wrong? I've just put, like when a murder you want to solve, you have to think all improbable possibilities. Of course, cosmological principle could be the one thing. Of course, this conference is on that, and which I think. But then, if cosmological principle is some problem, then why solar motion is coming different direction for CMB amplitude also, for quasars and other objects, and redshifts. So that is the thing. Okay, in case cosmological principle has some problem, then okay, time is up. So then, see, with cosmological principle we use this line element. However, if we want to drop cosmological principle, see in cosmological principle, Wales, whatever pronouncement be there, they postulate the infinite set of equivalent fundamental observers spread around the universe, and this is applicable to all of them. And we have a global time parameter, and then we separate the time from the spatial coordinates, except RT, which may be function of time. But if cosmological principle doesn't hold good, then even time will be function of r theta and phi. Then I don't know whether it can be solved or how you solve it. Maybe what AI or what you call machines? What machine? Thinking machine? No. Okay, whatever word I'm getting. Maybe that will solve it. Any case, so I had written a Urdu couplet that Hindi people or Urdu knowing people may understand. Hindi you can say क़यामत उनका अंदाज़े बया दास्तान कायनात आगाज़ का है इल्म ना अंजाम ही की खबर. In English you will say the style of storytelling there means cosmologists. This style of storytelling is deadly. Neither we know the beginning nor the end. Okay, that happens to every cosmological thing. Any case, this is just a way of greeting, and many of Indian languages I put here, including English. Of course, this is that Punjabi Namaste, that's my mother tongue. And this is Kannada, which is my mother-in-law tongue. My wife comes from Bangalore, so that's my mother-in-law tongue. And of course, Gujarat and Bengal and Vanakkam from Tamil, and Kashmir, Urdu, you can say Namaste in Urdu. So that's all.
Maybe questions?
Did you say what the amplitude of your redshift dipole was?
Pardon?
Did you say what the amplitude of the redshift dipole was?
Amplitude of?
Direction, but
Amplitude is turning out to be 4 times than the CMB dipole, about 1500 kilometer per second. Yeah.
Where are the redshifts obtained? Are the redshifts measured by the Gaia satellite? Is it
Yes, they have said so, which because Gaia was supposed to be measuring proper motions and all that,
but,
and these people have picked from that. Okay, and they say, at least in their paper, that these are spectroscopic redshifts. Okay, I tried to look how they measure, but I could not find. So I just took their word. And Gaia, of course, gives proper motions to small values and quite accuracy. So I don't think they would have got such a bias introduced in their proper motion or redshifts. But we don't know.
redshifts are different from proper motions?
No, that's true. But means not only proper motions, radial motion. Okay. But out of which they had 2 billion objects or so, they have found few million, okay, with high redshifts, which I think 6 million they had. These people then sorted it out and used some other catalogs and tried to weed out non-quasars.
Sebastian, do you want to comment on the Gaia selection function?
Oh, it may be off.
Just talk, we can hear you.
Speak loud. This one is okay. Hey, thanks for your talk. There are, okay, so the redshifts are obtained basically via the machine learning algorithm that the Quaya team has used. As part of this algorithm, they tried to learn the selection function on the sky, which is especially influenced by the, all of the things that Gaia picks up, even though it's a combination of Gaia and WISE that goes into their data. Their selection function works well for small scales, which is why they can retrieve power spectral information, and they do all sorts of analyses. On large scales, I think it's a bit doubtful. I don't know how that leaks into redshifts. It may be that the redshifts are just fine and it's just the number sources, as in the completeness on the sky, that is influenced by it. I don't know how the redshifts are influenced by it. But
these people, I forget the name, authors, they have explicitly stated these are spectroscopically measured redshift. I tried to go in that, but I could not find out. Then they have given reference to Gaia data, one of those. Okay, I went to that, but I could not easily find how it is. Then then they say this is the best sample of quasars.
Gaia had only photometric redshift.
they may have such a large
No,
number
they have
of
many photometric channels from which they can get. Yeah.
So I just wanted to make 2 comments. First of all, I think, as I stated before, I think Ellis and Baldwin is wrong because they assume spectra are power laws and real spectra are not power laws. And also, they're not flux limited, they are color limited. So that's about the Ellison Baldwin. But the other thing about qualia, so I mean, obviously, there is more dust toward the center of the galaxy than away from the galaxy. So all your selection functions would be biased by the galaxy, basically. So
Yeah, but dust, will it cause changes in redshift? See, number of sources.
we don't care about redshift. You're just looking at you're counting things. The redshift is nothing.
It won't change the redshift, although number of sources, what you see.
Yeah, you see fewer things
more or
towards the
less.
galaxy because
So
the
here number
extinction.
is not very important because we take what are quasars there, 1,000, 10,000, that's bin, we take the redshift.
Yeah.
Yeah, but that will be number of quasars, right? Not redshift change.
This is on the, that's the thing, this is not a number.
So that
counter.
doesn't matter, we
This is
take the
redshift
average redshift
distortion.
in the bin,
But it's
here as well as there.
redshift distortion. I don't understand.
And moreover, as the result seems to be almost same, whether you take 10 degree cut, 20 degree, 30 degree galactic cut, I take all sources beyond 30 degree and all sources within 30 degree also. Then also you get almost similar result. So
Maybe it's related to Nyayesh's question. So, I mean, galactic plane is extremely messy. I mean, that's why LSST is avoiding it. And even in gamma rays, you see a big glow in gamma rays. Okay, so, I don't know much about radio sources, but are we sure that the same problem is not there in radio sources, that there's not some background contamination in the galactic plane which is causing this?
But that's why I was saying I took the 10 degree, 20 degree, 30 degree cuts in the galactic plane, and the result didn't change. So beyond 30 degree, and in fact I took all sources within 30 degree. That also gave almost same result. So which was a bit strange, but in any case.
But what about randomizing? Okay, you did say you did simulations, right?
Well, those are simulation I did. But I also did
But not
cuts
bootstrapping.
in declination I did, which has nothing to do with galactic plane. 30 degree beyond declination, less than 30 degree, that also gave same result. So somehow it doesn't seem to depend upon the position of the quasars, at least not to first order. Yeah.
You mentioned doing slices with magnitude, apparent magnitude,
Yeah.
but did you also slice by volume by any chance and see whether
No, I didn't do anything.
the
on it.
volumetric
Like,
shells of quasars, would they?
No, because there I have to already assume some cosmological model to change redshift into distance. Or
That is true,
velocities.
yeah.
And I don't want to do that.
Okay.
I just took it, the data as it is.
Thank you very much.
Yeah, welcome.
Seems like
Yeah, shall I leave it here? How do you take it?
Next talk is online.
Hello, should I start?
Oh, hello, Pankaj. I didn't know you were online. So we having trouble to see you on the screen, so just give us 1 or 2 minutes, or even less, hopefully.
Hello?
Can you hear me? Maybe not.
Hello?
Hello, can you hear us? No. Okay, well, I propose we
Hello,
start.
can you hear me? Hello, am I audible in the, hello? No, not so far. Let me just connect again, just for a minute. Okay. Okay, let me try another route if it's not working. Just 1 minute. Hold on 1 minute.
Well, but it's, I think.
Yeah. I'll just try another one.
Well, let's start then anyway. So we have, the next talk is Pankaj Jain on theoretical model for large scale anisotropy. And then as soon as he can, then he'll start. He doesn't hear us, I think.
Hello, am I audible now? Oh, sorry. Hello, am I audible now?
Yeah, type in the chat.
Yeah. Okay.
Hello?
Okay.
Can you hear us now? So you can
Yeah.
start, basically.
Hello, can you hear us now?
I'm able to hear only from the mobile. Can you hear me? Can you hear me? Okay, so I'll share my screen, just 1 minute.
Excuse me, sir, can you hear us?
So, I assume I'm audible and you can see my screen. So I thank the organizers for giving me this opportunity to talk in this very interesting conference. I'm very disappointed that I was not able to come because my flight was cancelled. So the title of my talk is Theoretical Interpretation of Large-Scale Anisotropy in the Universe. So I'm Pankaj Jain from IIT Kanpur. So we have already heard about this, but there are large number of reported violations of large-scale anisotropy. There was this old work that we did, which showed that the radio polarization offset angles show a dipole anisotropy roughly aligned with the CMB dipole. This was Jain and Austin, 1999. Then there was also the very interesting observations that CMB quadrupole and octupole, they align with one another, and they also align close to the CMB dipole. It was done by these authors. And then you just heard about dipole in the matter distribution, which shows an excess dipole compared to the prediction from CMBR. This is, of course, we just did the talk by Singal. Also, a very strong signal is seen in the cat-wise data, infrared cat-wise data, work by Sipos et al. All of these, and there are also other effects which seem to point roughly towards Virgo supercluster. There's also this another interesting effect called the Hughes-Meekers effect, which we call it the Hughes-Meekers effect because it's done by Hughes-Meekers, and it shows that the optical polarization of quasars appear to be aligned over very large distances. So here we see a particular map over a large distance scale. This is in a redshift range of 1 to 2.3. Again, a very strong alignment is seen in the direction of Virgo supercluster. And also this additional claims, alignment of polarization and galaxy axis, seen also in radio. This is work with our group, also Taylor and Jagannathan, 2016. because of many claims, I'm not going to go through all of them. There's this very interesting work by Kaczynski et al. On large-scale cosmic flows, which seem to not saturate claims of isotropy in the Hubble constant, etc. And here I show a few of these. I will not update this figure. This is from 2004 actually. This is this our work on radio polarization, radio oxide angles. This is quadrupole optical. This is CMB dipole. This is the radio matter dipole, and so on. So all seem to be pointing in roughly the same direction. All seem to show a large-scale anisotropy. There's also additional effects, which goes by the name of hemispherical anisotropy or equivalently dipole modulation. This is the CMB temperature. This is by Erickson et al. 2000. So where they argue that they find in data that the CMB power is different in the two different hemispheres, and you can sort of phenomenologically explain that as a dipole modulation parameter, where delta T in some n-hat direction is equal to some isotropic field plus this dipole modulation term. And the signal is about 3 sigmas. The amplitude is found to be 0.072 plus minus 0.022. The hemispherical anisotropy, if you try to sort of explain this in terms of primordial density fluctuations, it's okay, hello? It seems to require an inhomogeneous universe. With the density fluctuations, we can express in this manner the correlation of density fluctuations, and we can express them in terms of relative coordinate and the mean coordinate. And if you have a model of this type, where you have a isotropic term which depends only on the relative distance, plus an inhomogeneous term that can explain the hemispherical anisotropy. I want to talk a bit about this dipole matter distribution. The matter dipole is expected to rise in homogeneous anisotropic universe due to a local motion. The observed amplitude, as Singal has explained, is much larger in comparison to the predicted dipole, seen both in radio and IR. Furthermore, the dipole also shows some other unexpected features. It shows a color dependence. So this is work by us, where we sort of took this IR envelope and we split the data into different color bins. This is the W1, W2 are different bands. So you have these different colors. So this one is, for example, from point A to point 9, and this one is higher color. So as you go to higher values of color, you're basically going to high redshift. So you go to high redshifts, and then it seems to. So what is very interesting is there is 3 points relatively close to one another, and then as you go beyond this thing seems to jump lower. In fact, all of this on the galactic plane now, and then it seems to move away. So this is the point at the highest redshift. The full data shows this one. This is the dipole direction shown in the full data. Both of these are somewhat significant, but the directions are completely different. So for large Z, the dipole lies close to the galactic plane. So next, we have heard about the relationship with local velocity, if interpreted as kinematic dipole. Of course, we seem to, what is seen so far, we cannot interpret it as a kinematic effect, but if we do that, then this is this work by Ellis and Baldwin, which we just heard about. So we assume that the flux follows the power law, S is mu to the power minus alpha. Assume, first of all, that the number counts also show power law dependence on S on the flux, and when the dipole is given, is related to the velocity by this formula. And then using this, once you measure the dipole, you can extract the velocity by using a mean value of alpha over the data, and this is one way to extract the velocity. But in fact, someone already mentioned this. This extraction is a bit complicated because neither the flux nor the number counts may actually follow power law. Furthermore, the alpha, it may not be reasonable to use a mean value of alpha, because if you see the distribution of alpha, it shows this very wide distribution, and there's no, it doesn't really show a Gaussian or anything like that. It would be reasonable to use a mean value. Therefore, it is best to set the velocity directly by simulations. So we've given the procedure for doing this, and this recent paper, and the velocity extracted in this way from the cat-wise data also leads to a high significance deviation from the standard prediction. There's yet another effect. In the same cat-wise data, we looked at anisotropies in different parameters. The x parameter, this is this parameter number function of s, this exponent. This parameter actually shows a dipole anisotropy. Amplitude is about 2.5 sigmas, and the direction is this one, which is somewhat interesting because it coincides with the CMB hemispherical anisotropy within errors. This is this. Of course, this needs to be tested further, but I mean, if the CMB power is different in two different directions, we could expect something of this kind to actually happen. It's not too surprising. So what we're seeing in finally there are two different class of anisotropies going in two different directions. Can both of these be physical? Let us try to think of a theoretical model which may explain spherical anisotropy. So we actually find that the Big Bang paradigm itself, within itself, has the ingredients to actually do this. This is because initially the universe may not be isotropic and homogeneous. Initially, the universe may be anisotropic and inhomogeneous. In fact, it is the isotropy and homogeneity during inflation. The inflation causes a small region to expand exponentially, leading to isotropy and homogeneity. So in figure, basically, in time, we expect the universe to be anisotropic and homogeneous. As inflation proceeds, it becomes isotropic and homogeneous. So our proposal is that the only inhomogeneous and anisotropies could affect observables at large distance scales. So the metric which was not quite homogeneous at that time, as it evolved, so for a long time, the inhomogeneity played a negligible role, but it could start playing a role at late times. Furthermore, the perturbations that are generated at very early time do not follow the cosmological principle, and they could be, now this one depends on the parameter space that you use, and depending on parameters, they could be entering the horizon in recent times and could actually lead to observable results. So both of these effects can lead to violation of the cosmological principle on large distance scales. So this was actually, this particular phenomena of how we deal with these perturbations at early time was done by Ackerman et al. 2007 and was taken up later on by us and recently by So the model that we want to propose is that we assume small inhomogeneity or anisotropy during the early phase of inflation. This decay inflation as expected, and of course this decay, as is well known, is explicitly demonstrated for anisotropic Bianchi models by the famous paper by Wald, not demonstrated for all possible cases. We assume that this is correct, and then we see what physical implications it has. So, as I already mentioned, we assume the universe enters an inflationary phase. It is described by a FRW metric plus a small perturbation. It's something that was done already by Ackerman et al. 2007. That formalism, in fact, they used the formalism earlier developed by Weinberg, and so we used that idea, and we used such a model plus the model that they had plus one more model. We used three different models which are anisotropic in this paper, and here this is basically FRW metric along with a small anisotropy given by this term. This term is assumed to be small, and as inflation proceeds, it actually goes to zero. And then recently we used a different inhomogeneous model which is basically like the scalar fluctuations. But here we are just, this is the actually background matrix. These are not really perturbations. Of course, we treat them as perturbations, but I mean, these are not the usual scalar perturbations. So we take xi to be such a sinusoidal function with pi equal to xi, and the expectation is that this perturbation becomes negligible as inflation proceeds, but as universe evolves, it could start playing a role later on. We can obtain the power spectrum in this slightly inhomogeneous universe by using the formalism developed by Weinberg. So we compute the power spectrum with this model by treating the inhomogeneous terms as small perturbations. The quadratic part of the Hamiltonian can be written as this is the standard isotropic part plus this additional part which contains the inhomogeneities. So this actually works out to be where psi is the perturbation term, this delta phi is the inflaton field. So you obtain this extra term in the Hamiltonian. And then this formula for computing the 2-point correlations is standard. The first term is the standard term in the isotropic universe. And then we have this additional perturbation term where you take this expectation value with the Hamiltonian and this delta phi. So this can be evaluated, and this gives you the kind of power spectrum we need, where the first term is the isotropic term, and the second term has this lambda dot x that I've already mentioned. So the inhomogeneous term, this one, leads to hemispherical anisotropy, and such a term leads to correlations between the CMB multiples L and L plus 1. So you can define this observable CLL plus 1 in this way, and then you can define a statistic SH which sums over L from 2 to some value L or whatever range you think will be useful to look at. You will look at such a range, and from that you can then fit to the data and extract the model parameters, which is what we have done. Furthermore, the background metric, as you evolve it acts like a FRW metric along with the supervisor perturbation. This can affect the CMB quadrupole nocturnal, which will impose some constraints on the parameter space. So taking all this into account, we can fit the data. Actually, there is a possibility of JWST between different parameters. So we just set omega equal to 0. This is the constraint due to the CMB quadrupole nocturnal, and this band gives you what you need to fit the hemispherical anisotropy. So there is a parameter range which actually is allowable. This is one parameter choice that we have given up here. Alpha is the overall coefficient, kappa is sort of like the wave number. So this is kind of the parameters which can explain the data. As it turns out, such a mode, which is basically actually the large wavelength mode, this can also explain the Hubble tension. This is something we explained a few years ago, also in recent work by Ashok. So coming to the theoretical model, so we see that a model can explain the CMB hemispherical anisotropy. Now the question is that, can it explain the remaining observations? So let me speculate. Now this is pure speculation. I'm sure you will be, you will have all kinds of issues with this, but let me never go ahead with this. So my speculation is that the excess matter dipole that we are seeing at low redshifts is due to local clustering, which may extend to distances much larger than 100 megaparsec. We don't expect it, but already there's data which indicates that this may not be, totally ruled out. So this can explain matter dipole as well as the old work on dipole radio polarization offsets. At larger redshift, the matter dipole shifts in direction, with the highest redshift dipole direction consistent with the CMB hemispherical anisotropy direction. So what I'm showing, I show this figure again. So this is the low redshift directions. In fact, it goes from here to to here, and then suddenly shifts down. And the highest redshift point, or the highest color point, which is interpreted as a redshift point, actually lies out here, which in fact is now agreeing with the direction of hemispherical anisotropy. So, of course, this could be just a fluke, but let's nevertheless speculate. So, this seems to indicate that as the highest redshifts, maybe the data is aligning with the hemispherical anisotropy is showing us. So, hence, aligning with CMB hemispherical anisotropy as a preferred direction may explain this. The alignment of CMB quadrupole noctupole can be explained by a suitable extension of the primordial model. The primordial model that we considered only had a inhomogeneous term, but we can also add a small anisotropic term, which could be aligned in a different direction. And so we need a model, actually I'm saying this today, we need a model which can reduce the power in a plane perpendicular to the preferred direction. And this can be done, and we have not done it, but this can certainly be done. So this can be accomplished by introducing a small anisotropic perturbation, which was used in Rath et al. Paper long ago in our inhomogeneous model. So this assumes that we should be able to explain both the hemispherical anisotropy and the CMB quadrupole noctupole alignment. And if you trust the results that the matter dipole is also pointing in this direction at large redshifts, then perhaps we can explain that also. And then in this picture, the CMB dipole will be dominantly of kinematic division. And the generalized background metric may also explain the Hubble tension, which we seem to be seeing, already in our analysis. Then there was this issue of alignment of polarizations over large distances. This might be explained by spatial correlations in the primordial magnetic field. So if you include primordial magnetic field in your large-scale simulations, cosmological simulations, they might align galaxies with one another and also align galaxy polarization with one another. So this is possible. This is maybe possible. It's something we have actually speculated already in these papers. So I conclude my talk. There's considerable evidence for anisotropy in the universe. There seem to exist effects pointing in two almost orthogonal directions. We have presented a speculative model which may explain both many of the observations, and that's all actually. And I just have a list of my collaborators. And thank you all very much. So I don't know if I can hear you. I can do one thing. I can just open the just 1 minute. Let me.
Okay, let's.
Hello,
Can you hear me?
can you hear us?
Okay, I've opened the live streaming now. If somebody speaks, maybe I should be able to hear it from there. Okay. Yes. Yes, I can hear you.
You can hear? Can you hear me?
Hello, can you hear us now?
Okay, there's a bit of a. This is going to be a problem. This is not going to work. Sorry.
Can you hear me? Can you hear me? Yeah, I can hear you. Can you hear me? You're muted.
Yeah, you can speak now. Can you hear me now?
Yes. And can you
Okay,
hear me?
great. So now we can connect directly. Wonderful. Go ahead.
Okay. So thank you for the very nice talk and for the interesting proposal about how to explain some of the statistical isotropy violation anomalies. I was wondering if you could comment, because it seems like the model you have would give if it gives a low variance north, would give a high variance south. That's the first thing, and which is not something we see. And the second thing is, I'm trying to understand how you would get a quadrupole and octupole that are purely planar perpendicular to the dipole from this, unless this mechanism. In particular, there would have to be, I presume, no primordial, other source of primordial fluctuations at the low L's. Is that what you're saying? And that would produce a quadrupole and octupole with a larger octupole and a smaller quadrupole that are purely planar and aligned.
Yeah, okay. So this is something we have already shown in our paper in 2013. Actually, the effect is statistical. So if you have a sort of an anisotropy where there's some sort of a quadrupole power, additional quadrupole power generated in the CMB. So that direction of the quadrupole you can select, and so that can point in this direction, which will just cut the power in the plane perpendicular to, so how did it go? So yeah, so the power in this direction was small, right? So that, yeah, right, exactly. So the power in the direction of the quadrupole and octupole was actually small, and all the hotspots lied in the plane perpendicular to it. So there's a quadrupole anisotropy that you pick up, and that can cut the power in that direction, and that can align the quadrupole and octupole.
So the quadrupole is almost perfectly perpendicular to the dipole direction. You have a series of maxima and minima that are in along a great circle on the sphere that is perpendicular to that's at 90 degrees to the dipole approximately. And an octupole.
Which dipole? It's not 90 degrees to the dipole. I don't.
Yeah.
I see. No.
The plane of the quadrupole and octupole is perpendicular to the dipole.
It's perpendicular, yeah, but actually the axis points perpendicular to this plane. So in this plane you have so that is a sort of like the axis of the quadrupole.
Yeah, the dipole is close to the axis of the quadrupole.
Right,
and the octupole.
So there's a quadrupolar, there's an additional quadrupolar anisotropy. There's a small perturbation that I'm introducing, which is giving you a quadrupolar anisotropy in this direction.
So you have to add
that's going to cut the power.
You have to add
that's
that by
cut
hand.
The power in this direction. Excuse me?
So you have to add that by hand, and then you
yes.
And then you get an octupole that just happens, that is bigger than that in some sense. It's not a perturbation of the quadrupole.
Mostly, see, most of this quadrupole and octupole are just the standard. This additional thing is a small perturbation.
Right,
so
but
it actually, yeah.
But the quadrupole and octupole are almost purely in that plane. It's not like some additional correlation. They're almost purely in that plane.
Well, I mean, okay, this effect is statistical.
No.
So, I mean, so one has to see. I have to go back and now check the parameters. So, the power is not zero in that direction.
The power is almost zero.
The hotspots are all lying in that plane. I agree with that, but it's not as if the power is exactly zero in that direction also.
Well, it's actually quite close. Whether you look at that from the De Oliveira-Costa axis that maximizes the angular momentum dispersion of the quadrupole and octupole, or you look at it in the multipole vector formalism, you find that the quadrupole and octupole planes are almost perfectly aligned with the three octupole planes, and the quadrupole plane are almost perfectly aligned within I think 10 degrees of each other, and nearly perpendicular to the dipole, nearly parallel to the dipole.
Okay, fair enough. But I think this is something I don't have the actual values for myself. to the best of my recollection, this I think we settled in our 2013 paper. It's suppose statistical. The effect is statistical. It is, I mean, it is not that it has to happen, but I mean, statistically, this was acceptable as an explanation for the quadrupole and octupole alignment. That's what I'm really meaning by this.
Thanks.
So I will certainly be happy to, write to you more about, exactly what we found in that direction.
All right. Thank you very much for your talk. And now, because we're late, we're going to move to the next talk. Thank you.
Okay, thank you very much.
Yeah, go ahead. So the next talk is Aseem Paranjape, and is going to speak about the model-agnostic cosmological inference from the redshift space BAO features. Paranjape.
Use this mic? Or? Is this okay? All right, thank you. And thank you to Tarun, who is not here, and Subir, and all the organizers for arranging this invigorating meeting and for inviting me. So when I was thinking about what to present, I picked this topic on work that I've been doing with Ravi Sheth, who sends his regards to all his friends in the audience. We've been working on this for the last few years. And after listening to all the talks on the bulk flows, I thought it might resonate even more with several people in this audience. So the idea is to do model-agnostic cosmological inference from the redshift space BAO feature. I will discuss what I mean by this. So I think for this audience, I don't need to introduce what the BAO feature is. There are acoustic oscillations, sound waves in the early universe. This is what leads to the primary temperature anisotropies of the CMB, and the standard model predicts that we should see an imprint of the same sound waves in the spatial distribution of galaxies at late times. And because the scale of the sound horizon at last scattering is what is supposed to be imprinted in the galaxy distribution, this scale has the potential to become a standard ruler. This was recognized long ago. I stole this plot from this very nice paper by Stefano Anselmi, Glenn, and Ravi, who pointed out that it's not just the location of the peak, but there are other features, including what they call the linear point, which might be very nice and robust standard rulers that can be used for cosmology. So this feature has been detected now almost 20 years ago, and BAO science is evolved just like the field, the cosmological field is evolved. This is what the feature looks like when you measure it in the two-point function of galaxies. And it's a 2D plot because observations live in redshift space. And in redshift space, there are peculiar motions, and these peculiar motions distort the feature along and perpendicular to the line of sight. So what you see, what you might have seen as a circle in this two-point correlation function in 2D becomes distorted into this kind of feature here. And at smaller scales, you see the Kaiser effect. Because this is an anisotropic signal, it is useful to characterize it in terms of multipoles. So people define the Legendre polynomial expansion, the multipole expansion of this feature. And that is what is now measured. It has been measured for a while. The first measurements were just of the monopole. Now we have the monopole as well as the quadrupole being measured. Hopefully with DESI, the next order, L equals 4, which would be relevant, might also be measured. This is with BOSS DR12. Okay, so like I said, you want to use the location of this feature to do cosmology. And now, because you're in the precision regime, you want to make sure that you've handled systematics well. So it's a question of saying, I expect a peak in the data. How do I determine the location of this peak with very low errors and with both statistically as well as systematically. There is a well-developed pipeline that people typically use for this, which I will not go through in detail. This is not my work. It is what is used by the DESI collaboration and previous collaborations. It was developed and refined for SDSS and its descendants. The takeaway message from this description is that the pipeline starts with a template for the feature, which assumes a cosmological model. And typically, one assumes lambda CDM. Not only that, one fixes the values of the parameters of lambda CDM. They call it the fiducial model. And the underlying assumption is that the real universe, whatever it is not very far from this fiducial template. This is the standard approach that one is taking here. And when you go through the details, you find that there are two important cosmologically relevant parameters which tell you how much the feature has moved along and perpendicular to your line of sight. So these are these two scaling parameters. Along with this, there are of the order of 15. In this particular example, there are 15, but it could be around this number. 15 nuisance parameters which describe what is called the broadband shape of this of the two-point correlation function surrounding the peak. Okay? And then you plug in this model which starts with this template. You propagate it onto this plane of the data. There is again the monopole and the quadrupole for a variety of different samples. This is DESI DR2. And I think what are shown as the solid lines are the best fits that you get from the results of such an analysis. Of course.
Why is the correlation function rising at large separations?
In some data sets. No, you mean the quadrupole?
Yeah.
So the quadrupole, I will show you this because it is a projection onto Legendre polynomials. So first, it is not even something like the power spectrum, which is positive definite, etc. Right? So it's a complicated beast. True, and the standard model will also show you that. I'll show you some plots. It is not it is not surprising.
That doesn't matter. It should die down. It's a two-point correlation. You're assuming homogeneity at large scale. Yes, the IOPI will die down.
I think what you can see here is that these are negative values. So the rise, it's the quadrupole. So the quadrupole is not necessarily positive.
The quadrupole.
Yes. Yeah. You're talking about the monopole here. I think, so this is...
That was a recurrent systematic in SDSS, and I wanted to see if it is still there in
I see. So let's differentiate between the data points and the best fit. The best fit comes from some template which has a broadband non-cosmological thing that they're trying to model. Who knows what it's going to do, right? It goes out of control after some point. The question is whether the data up to the point that you've measured are consistent with some reasonable expectation from theory. Yeah? Okay, so this technique, by the way, there is another set, and there's another whole literature associated with something called reconstruction, which works at the field level, where you try to narrow down the impact of nonlinear broadening. I will discuss this quite a bit in detail, but I will not go into what is usually done in the name of reconstruction, because even after doing what people call reconstruction, you end up doing something like this anyway, a template-based fit to recover the location of the peak, and then the location of the peak is then used to do cosmology. This kind of procedure leads you to measurements eventually that look like this in terms of these distances to the redshifts that you're talking about, and that gives you a way of converting into the Hubble diagram, and therefore then whatever we have heard about in this talk, in this conference, on saying that there are departures from lambda CDM. So at this point, it's worth taking a pause and saying, okay, we started with an analysis routine which assumed lambda CDM with a template and assumed that we are not very far. But now we are finding at least statistically significant departures from lambda CDM. So perhaps one should pay a little bit of attention to the way we have done things and check that everything is self-consistent, and also ask whether we can do things better. Because even if I don't worry about this particular parameterization of dark energy, etc. Suppose my goal were to say I have my favorite model of modified gravity, and I want to use these beautiful data points to constrain this model. There is no easy way right now of directly taking my model and projecting it onto this plane, because most of the analysis that is done involves a template. Okay, and that template is ΛCDM. So can we go away from this paradigm of a template-based, of a cosmological template-based analysis? So can we do better? So in order to do this, I will like to frame things in the language of bulk flows. And here, this is the linear velocity power spectrum, okay, in a Planck 18 cosmology. What you see immediately is that there is a peak around 0.02, 03, something like this. So of the order of 50 to 100 MPC. What is this saying? What this is saying is that velocities, cosmic velocities, are correlated or coherent on scales of 50 to 100 MPC. So this is a coherence scale. And now these are velocities. So velocities move things. So you can ask, how much do they move things? That is given by the integral over this power, which is a dispersion. And that dispersion is a number of order 10 MPC over h. So the picture is that there are these circles in the sky, which are the scale of interest. It coincidentally happens to also be of the order of the BAO scale. Okay, the BAO scale physics comes from the sound horizon at last scattering. It's baryonic physics. It need not have anything to do with this coherence scale in principle. Okay, so this is a bit of a coincidence. But imagine there is a feature at these large scales. It happens to be the scale at which bulk flows are correlated. That means I have patches of mass which are moving around randomly by amounts which are of the order of 10 MPC over h. So if I take a sharp feature, which is imprinted as circles in the sky, and I randomly move these circles around by of the order of 10 MPC over h, what I expect is that the thickness of my feature will increase. I'll smear out my feature. It's like taking a sharp feature and adding Gaussian noise to it. Okay, and this noise is not coming from small scales, satellites in clusters. It's not that dispersion. These are coherent flows which are moving around by small amounts. So this smearing is very naturally expected. And this was worked out long ago by Somnath Bharadwaj. I think, I don't know, you guys may know, was he here at the time in 1996? He was around somewhere. So anyway, so he worked this out in a nice theoretical calculation, which was again seen by Martin Croce and Roman Scocimaro in a beautiful series of papers in 2006 to 8 on renormalized perturbation theory. And what you show here is that if you just consider dark matter in real space, without worrying about redshift space distortions and observations, etc., what you expect is a Gaussian smearing of the linear theory two-point correlation function with a smearing scale sigma v, which is exactly the same thing that I was talking about before. It's the integral of the velocity power. Okay. I'm ignoring some effects here, which I'll keep writing this down. I keep ignoring it up to a point because this will become important as I go along. Okay, so this smearing is expected. So this leads to a nice idea, which Ravi and collaborators, Farnik Nikakhtar was a student at the time, Ravi and Edith Zehavi are on this paper. And they pointed out that if I expect a smearing of the two-point correlation function, which if I convert from my usual k-space way of writing things to a real space way of writing things, it's just a Gaussian convolution. It is going to change the nature of the peak. It's going to broaden the peak. It will also do interesting things to the location of the peak, to the location of the dip, to the location of the linear point, etc. But the other very interesting thing that it does is that suppose I say that I want to be completely agnostic about what this linear theory two-point correlation function is. I don't want to assume ΛCDM. I am just interested in modeling it in this range of scales. It sort of looks like an S shape. An S shape can be very easily produced by a polynomial. So I assume that my linear theory shape is a polynomial. I can just analytically do this Gaussian convolution, and I get something that involves some complicated functions, but they are analytical functions. In this case, the generalized Laguerre functions. Okay, there's exponentials, there's an error function, there's polynomials. Okay, something, but you can write it down by hand. And the beauty of this is that this is now supposed to be a model of your late time correlation function. So I can, in principle, apply it to data and extract these coefficients and then simply apply them to the monomials that I started with, and I get reconstruction for free. No assumption of cosmology involved. Yeah? One caveat, the plots that I showed you with the data where I have two-point correlation function as a function of separation in megaparsec assumes a conversion of redshifts and angles to distances. But this conversion from redshifts and angles to distances is like saying I would like to work in MPC units or centimeters or kiloparsecs or whatever. It's a choice of units, right? So as long as I pick one number to do that conversion, I can always undo it whenever I do the cosmological analysis eventually. So that's not really important. This is the nice feature here that I can convert the shape of this feature into a model agnostic description, which allows me to very easily go from the nonlinearly evolved observed feature into the linear theory cosmological feature that I'm interested in. Yeah, Subir and then.
Velocity dispersion was also computed in a model, right? It's an integral over.
I will talk about keeping this as your primary free cosmologically relevant parameter. Whichever model of cosmology you would like to work in has to give me some estimate of this number, and data will then tell you. Yeah. It's a number. We will discuss this. I'll come to. I hope I will come to this at the end of the time. Yes, Niyash. It is a deconvolution, exactly, and this is a simple way of doing it. If I pick a simple basis, then the deconvolution is trivial. I don't have to do anything, because I just need to know how my basis gets propagated into the convolved space. Yeah. Okay?
And the velocity thing is also computed assuming Gaussian field. So this is only true on scales large enough that
this is not assuming, this Gaussian convolution is not a statistical effect. It is a dynamical effect due to bulk flows. So the bulk flows produce a Gaussian effect due to the e to the minus k squared in Fourier space. Yeah. Yeah. Yes, Glenn? Yeah.
Aseem, you'll notice that Stefano and Selmy and I didn't join this paper, not because we weren't part of doing the work, but because, and not because we thought the mathematics was wrong, but because we couldn't see the point of this in the data now.
Very nice. I hope we can discuss this, and I'm trying to show you how to take this to data. I agree with you that this paper is not enough to be applied to the data. Is that fair enough? So my claim is that this is a nice idea at this stage, and if I just stopped here, I cannot convince anyone that I can do anything with this in the data. I'm trying to take you to the data. That's the rest of the talk. Yeah. So at the end, we can have another debate about this if you like. Okay, so this is what I would like to do. I need to include the effects of redshift space distortions because the whole idea was in real space until now. I also have to worry about effects of scale-dependent bias and mode coupling. I have not told you what these are, but I will convince you that they are important. And I also need to worry about what Orko was talking about. What is an optimal basis to do this convolution exercise in for the linear theory? All right, so let's talk about the redshift space part first. This is the easiest part of the calculation actually because these results have also been done. The same kind of RPT analysis that allows you to do the real space smearing tells you what to do in redshift space. Now in redshift space there are two directions. So basically the dispersion along and perpendicular to the line of sight becomes important. And you can show that you replace your Gaussian isotropic kernel with an anisotropic kernel with these dispersions. And your linear theory also picks up a Kaiser factor. All right, so there is this. So I can now, at least if I use the crutch of ΛCDM to try to understand what my feature looks like in redshift space, I have a description of this. Okay, so I will use this to write things down in a way which can then be converted into this model agnostic form that I was talking about. Okay, so this is what happens. You start with a Fourier Bessel representation, which looks like this particular integral. It has a smearing, and it has the Kaiser effect. And the key approximation now is to realize that there's a separation of scales in the problem. I am worried about the feature at 100 MPC scales, and I have a smearing scale which is 10 MPC. So there is a large separation, it's an order of magnitude separation, which I invoke to replace this integral with this form. All right? So there is a complicated integral over exponentials, etc. You could do it analytically as well, but it's useful, I will argue, to write it in this form, because when I get it to this form, you see what is happening is that I've thrown away some higher order terms in K, but what is left looks exactly like another smearing. It's a slightly different smearing of the linear function, of the linear 2PCF. So earlier we were okay with the real space smearing. We said bulk flows are going to smear the linear 2PCF in real space. What I'm claiming is that because of the separation of scales, even in redshift space, there is a smearing of the 2PCF. And these coefficients here, these effective smearing lengths, can be easily derived from, just from analyzing what this thing does when I do a k-squared expansion. Again, I'll not go into the details here because they're not important. But the point is, once I get it to this form, my monopole, quadrupole, and hexadecapole can be easily written in terms of the same function, which was this Gaussian convolution, now appearing with different smoothing scales, smearing scales. Okay, and there are some complications due to integrals, volume integrals of this thing. Come again? F is the, sorry, where do you see this one? Oh, sorry, this is the linear growth rate, d log d by d log a. So beta here was F over the linear bias. It's the same F. Yeah, okay. So this is again a nice form because there is only this function appearing everywhere. It's just evaluated with different smearings, okay? And this one, we said we can approximate in this way. Yeah, so that's where the model agnostic thing has an anchor, and it's the same parameters which repeatedly appear. So if I pick a fifth order polynomial or something to describe this, the same fifth order polynomial goes into all of them. So now if I have a collection of measurements, I can try to fit everything at once, and I improve my constraints in principle. Okay, so this is one thing about redshift space distortions. So we call this the Zeldovich smearing approximation, which allows us to do this. Actually, Hamilton in 1992 had exactly these equations. It's just that his equations didn't have a smearing. So if I just set sigma to 0 in all my expressions, I will recover Hamilton's equation number 8 or something. And this is what this looks like. I've made an approximation here, so I should check what this compares with when I just do the, the full integral here. And you can see that the full integral is given by these solid lines. So for the monopole in red, and the dashed is my approximation. So the monopole in red, the approximation does quite well. For the quadrupole, I see large departures. For example, the quadrupole has a 0 crossing in the exact thing, and my approximation is not doing that. And the hexadecapole has some other effects. And basically, these are the values of my effective smoothing scales, smearing scales, and you can see that they increase as a function of L, and that kind of explains why I become progressively worse as I go to higher and higher L. So this is where I want to point out that in principle, okay, you could take this plot and say this is the level of approximation that I'm talking about. However, what I am calling this exact model here, especially for the quadrupole, I should also check with simulations whether it actually is a reasonable model or not. That is shown here in the right panel. Again, red, green, blue are the same, the same color scheme. This is taken from a paper by Jan Grieb and company. And what you can see, especially in the quadrupole, it's slightly different cosmology, etc., and slightly different quantity on the y-axis. But just pay attention to the fact that the blue curve here goes through 0 around 0.1 or so, or 0.2 or so. Okay? Whereas at 0.2, these blue data points are substantially above 0. So the simulations have much more power than my model here. And what we believe is that this is because we have completely ignored what is called scale-dependent bias, which will add power at small scales. And we have just assumed a linear scale-independent bias. Okay, so this is an important effect because it is just it is changing the behavior here. And this was one of the things that we wanted to figure out. But before I come to that, suppose I just ignore scale-dependent bias, and I try to ask, can I convert this into a cosmologically interesting inference exercise? This is what you get. So this is some toy data generated using these solid curves, okay, just Gaussian random sampling of these solid curves, and then analyzed assuming my Zeldovich smearing approximation. And I know the truth that's given in the yellow points, and I do an MCMC analysis on this data to try to recover these true values. And you see that for BOSS DR12, I can sort of recover things quite well. For DESI LRGs, I would not be able to do it, primarily because my approximation here is breaking down. So there are two things which are happening. The approximation is breaking down, even if I assume just a linear scale independent bias. And this model itself, that means the base model for this data set itself is incomplete. But the important takeaway from this plot is that I would argue that the BAO feature should be used in this way. These are the parameters that can be constrained in a model independent, in a model agnostic manner with the BAO feature. The first one is the growth rate. The second one is the smearing scale, sigma v from linear theory. And this is a compression of all those basis coefficients that I was talking about. In this particular case, I compressed them to just recover the value of the linear point. So I've reduced it to one number. In principle, it is as many numbers as you modeled.
But Ravi, Stefano, and I managed to do that without this reconstruction on the bottom.
What we showed, I think, in our first paper, which I will not discuss here, is that the error bars that you get from polynomials will be slightly larger than the error bars you get with the reconstruction.
But fewer model-dependent.
If you say that, if you say that I don't believe that there is a Gaussian smearing, so in that sense I'm not making as many assumptions, then yes, I agree. Here, the idea is that I'm not just interested in those coefficients. For me, those coefficients have been squeezed. I chose to squeeze them into the linear point. But now I get information about sigma as well, right? And that's a very interesting cosmological parameter as well. So we should not throw it away, was my point of view. Yeah? Okay.
What does the simulation know about scale-dependent bias? What sort of simulation?
These are n-body simulations, and there are halos. So they have done the full nonlinear growth the way they want to. And now we have chosen to model them as linear scale and independent bias. And I'm claiming that that is incorrect. Okay? Sorry, there was another question? Yeah.
So, I don't understand. It seems to be there's a perfect degeneracy between the underlying power spectrum and this Gaussian suppression and the multiply rate. So you do this basis expansion with artificially direct degeneracy, but really there's a free function multiplied by Gaussian, so they're perfectly degenerate to each other. I can direct it.
Degeneracy between what and what?
Sigma,
Sigma is one number.
and then the free power spectrum, which is one function.
Yes, but the power spectrum is one function, right? Sigma is one particular integral of something related to the. No, so in lambda CDM there is a perfect degenerate. They are related to each other. So I am more model agnostic here because I'm saying that I'm not assuming that these two are necessarily connected to each other. Yes, and that basis doesn't come from a cosmology, so I'm being model agnostic in that sense. I'm not forcing my basis to know about sigma. I'm treating sigma as an independent parameter. Sebastian.
On the previous slide, you had a function from which you sampled the generated object.
Yeah. Louder, please.
Would you not want to take one of the past simulations because this delta on the left?
Don't take this too seriously because I'm telling you that this is anyway wrong. No, I mean this solid curve is anyway not a good description of real simulation. So I want to. This exercise was just to see whether I can push everything forwards and bring it to the space of the data. I'm not claiming that these are the constraints I will get. I agree that you should compare with simulations at the end. Yes, yes, I agree. Yeah, absolutely. That's what you should do. This is a simplistic analysis. let's talk about priors later. I would like to discuss more relevant things just now. Yeah. There is a little point here. That's a pretty important point. This is the integral of the monopole power spectrum, which we use as a way to anchor sigma v. That's the main place where the constraint on sigma v comes from. Yeah? And its full covariance with this thing is taken into account and so on. Shall I go on? Yeah. Okay, so scale-dependent bias is missing. Peaks theory gives us a way of understanding scale-dependent bias. And Peaks theory plus the idea of bulk flows, right? So this is Zeldovich Peaks theory. And this started, of course, with BBKS, and it has been developed further over the years. And basically, I will not go into the details, but what you can do using Peaks theory is to motivate an expression for the scale dependence of bias, which looks kind of like this, where you say that instead of just having a Kaiser factor that has a B plus something that depends on the angle between the K and the line of sight, I really should be talking about a Lagrangian bias for the density, and as well as a velocity bias. Okay? And both of these are expected to be K-dependent. And Peaks theory will make predictions for peaks of a given scale, how that K-dependent behaves. Now, in principle, you should propagate this forward with a model for abundances of peaks, et cetera, et cetera. All of this becomes very model-dependent. So what we played around with was several different ansatz for trying to capture the essence of this scale dependence. And we settled on this very simple one, where I have a k-squared piece and an exponential and a Gaussian piece. The Gaussian piece basically tells me about the typical scale of the masses of the peaks. And this k-squared is basically telling me how density differences at around peak locations and the velocities play a role here. Okay, so these are kind of motivated from Peaks theory. This Gaussian shape is mostly for simplicity. The nice thing about this model is that there is a k-squared at the base level and a Gaussian expression here. This plays very nicely with our approach of trying to take everything to configuration space, because this just looks like another smoothing, which will add to my smoothing kernel. And this one just becomes a Laplacian. So whatever I had, I had my model agnostic basis, I smoothed it out, and I got something that had Laguerres or whatever they were. Now I just have to take Laplacians of those. Everything is spherically symmetric anyway after taking multipoles, so taking Laplacians is also very easy. Okay, so it's all completely analytical, which is why we like it. It, of course, comes at the cost of additional parameters. And in this case, the scale-dependent bias introduces 3 new parameters, this capital B1, capital BV, and R star. This RP is not really a parameter, it's just a pivot scale to help me set units. Okay, but there are 3 parameters here. There's another effect which may or may not be important. Its importance has not been pinned down in the literature. It has been discussed quite a bit. This is the effect of mode coupling. This is the idea that in perturbation theory, for example, I will have a coupling between long wavelength modes and short wavelength modes because my theory is nonlinear. And how much this coupling is important at the BAO scale is a matter of discussion. So there have been indications throughout the literature that this effect should be small. But now, since we have a model which doesn't work, and now we are trying to modify it, so then we said, okay, let's try to be a bit careful about this as well. This is probably the most complicated of all the effects to model, and it turns out to be the least relevant, okay, because it turns out that making reasonable assumptions about its behavior leads to an effect which is much smaller than all the other effects that I'm talking about. So if you're interested in this, I will be happy to discuss the details, but in the interest of time, let me skip over the mode coupling piece. But just to summarize, I now have a model in which I have an agnostic way of including the effects of scale-dependent bias, which is in this capital B here, as well as mode coupling. Mode coupling brings in principle, 2 additional parameters. You can actually show that this RMC is expected to be basically the same as the sigma V that we were talking about. We treat it as a free parameter just to confirm that our expectation is valid, because there are several assumptions involved. Okay, but now I would like to, so this can be put into a model agnostic framework in principle. But before that, I want to see whether this way of describing scale-dependent bias and mode coupling actually works well with simulations. So maybe this answers a bit of what Sebastian was talking about. So now these are n-body simulations. So this is the 2-point function multipoles in n-body simulations. And what I've done is to take my scale-dependent bias plus mode coupling. That's what I call SDBMC, scale-dependent bias and mode coupling. And I compare it with the simulations. I get constraints on my model parameters. For example, one of the things you see is that the mode coupling scale is 6 MPC over H. This is exactly the value of sigma V for this cosmology. Okay, so this is a validation exercise. I fix everything except these parameters because I know what the cosmology is, I know what F is, sigma V is, etc. And I see whether the fit works, and it produces a reasonably good fit. I motivated this whole thing by showing that in Fourier space, I had excess power where my original model was going down. So it's good to check that this also happens in Fourier space. And you can see that in the Grieb et al. Simulations, if we compare with those, the model doesn't work beyond a certain K, which is not surprising because at extremely nonlinear scales, we are not expected to work very well. So we pick a scale out to which we work well, and we ask what is the comparison between the best fit SDBMC model with the model without these effects. And you see this is what I was talking about. The model without the effects produces a quadrupole which has a zero crossing around 0.12 or so. The data are above, and our model also remains above to pretty small scales. Okay? So this builds some confidence that there is some merit in using this particular model. All right. So in the last 5 minutes or so, let me turn to this choice of optimal basis. So what I've told you is how to include redshift space distortions, how to include scale-dependent bias and mode coupling. Now, what do I do with my optimal basis? This was my favorite paper to write. Okay, this one. This is the first one that where I started working on this topic with Ravi, where we showed that, okay, at least if you know everything, right, if you work in the limit that you guys were working in, where I don't worry about trying to constrain the value of sigma V. I just use it as a free parameter if I choose to do it with smearing. Then I can do a simple Bayesian exercise for picking which polynomial works best. Okay, so the order of the polynomial for a given data set. So this Bayesian exercise is actually useful even when you allow parameter space to increase, although the model becomes nonlinear, so it's less easy to calculate these Bayes factors. We can have a discussion on this later. But what we were worried about is that the monomial basis, especially as you go to better and better data, with DESI, for example, the toy models that I showed you already had a 9th degree polynomial that we were fitting. If the data errors are going down, then my number of parameters in the polynomial are increasing. And what we also see, which I have not shown here, is that most of these parameters are either very degenerate with each other or actually not even detected with high significance. So many of them are consistent with 0. So in principle, what this is saying is that there is another basis which is better probably. And if you could only find what that basis is, then you would be able to work with a smaller number of functions. Okay? So we approached this problem. This was my first foray into deep learning. We said, let's just learn these basis functions for a range of cosmologies. And the idea was to take a 2-point correlation function in lambda CDM and just write it in a way that separates the cosmological parameters theta from the dependence on the separation r, and just learn what these functions b of r and w of theta are. Okay? And you can do this in a neural network setup. And what you find are these very nice, interesting basis function shapes. It turns out that there are 9 of them which work well in the noise-free regime. And when you add noise, this number will most likely go down because not all of them will be relevant, most likely. Yeah? So this is like for the perfect measurement of Xi linear, I can describe it with 9 coefficients, with 9 numbers. Yeah? One of them is the constant, and there are 8 non-trivial functions. The shapes are very interesting. Some of them look like the 2-point correlation function. Some of them look like its derivative. And there are all kinds of broadband shapes that are happening here. Okay? So ask me about this later. Since I'm out of time, I'm almost done with this. This is just to show you that the basis function works well. I'm comparing the ground truth with doing a least squares calculation. When I have a basis set, what will I do? I'll take my data, I'll do a least squares calculation and extract coefficients. And now the best fit that I get for my function, I can compare it with the ground truth, and I ask, how well could I describe the function? And I can describe the function pretty well. Okay, so I will leave you here. I have in this program that I have described, where I would like to do a model agnostic description of the redshift space BAO feature. I've shown you how to include redshift space distortions. We know how to at least approximately but sufficiently accurately include the effects of scale-dependent bias and mode coupling. All of these are independent of the choice of cosmology, provided you work with the correct parameterization, which includes f, sigma v, and the basis coefficients, which you can compress into, let's say, the scale of the feature. I discussed the optimal basis as well. This is something that has been pending. I have the notes ready. But now in this meeting, I have been, as I said, invigorated and refreshed. The idea is to go back and put all this together. Okay, so thank you very much for your attention.
Thanks very much for your talk. Two very quick questions. The first is, with this formalism, in principle, you could get an analytical expression for the reconstruction covariance matrix, not the full covariance matrix, but just the reconstruction part.
What do you mean by the reconstruction covariance matrix?
So the noise or the scatter introduced by the action of reconstruction. In this case, the reconstruction is the fitting of your functions and focusing on the linear point and its motion as opposed to the BAO template. And just before you answer that, the second question is about the basis functions you mentioned at the very end. You didn't really need a neural network for that, right? I mean, you can compute the Bayesian evidence for 1, 2, 3, 4.
Very nice. So let me take the second question first, because the first one I didn't understand. I'll ask you about that later.
Sure.
The idea here, so these basis functions were extracted by varying only omega matter and h in a flat lambda CDM cosmology. I just allowed omega matter and h to be on a Latin hypercube, and I get my two-point correlation function, and I try to emulate it in this way, right, where I have separated the effect on R. So now I extract this dependence on R, and now I compare it with a Latin hypercube in which I vary omega matter, H, AS, NS, omega baryon, omega curvature, W. Okay. Most of these are just amplitudes, but NS and omega B are very important new functions. And what you can see in this stringent test is that I achieve sub% accuracy here as well. So the hope now, because of this exercise, the thing that excites me the most is that in principle, I can now run a modified gravity code like high class, or I can switch on neutrinos in class, and I can try to use the same basis functions to describe those variations. And if that happens, then I'm truly model agnostic, because now I can describe, with these functions, I can describe those cosmologies which the functions never knew about at all.
Oh, okay, then I actually missed that point that you're connecting with cosmological.
I didn't say it. Yeah.
Truly model agnostic is also just within the set of models that you're looking at, which in this case, in the color of many of these talks,
you keep building, of course.
Are the isotropic
but
models,
you see,
right?
No, but you see here, at least from flat lambda CDM, omega matter, and H, I have gone to curved WCDM.
Yeah.
So in that sense, everything is nested, I agree, but it's still a wide parameter space that the same basis set is capable of describing. Sure. So there is hope for this technique.
Well, just a quick question, and then hopefully there's a further direction in this. How do they take out since one's using many galaxies to do this, how do they take out the asymptotic bias?
What is the asymptotic bias?
Well, you're dealing a lot with the attempt to try and, because my second part of that question is, it's not B of K, it's basically BI of K, where I runs over galaxy types, and they all differ.
Sure. Yep.
So the question is, does that scatter in to the
very interesting.
To the form?
Yep.
Because, as you know, things like anomalous gas physics are going to modify that, and it's probably going to be dependent on the type of galaxy. And so asymptotically, it seems to always be that the response function will go to the asymptotic bias. But even that's not clear because you could have non-Gaussian elements, which is what I'm really going to try and get you to go to.
Yeah.
But I'm just wondering whether you've done the checks on the different
So
elements.
I suppose, so maybe if I write things in this language, so there is a constant which will remain as k goes to 0.
That's right, but it's a different constant for different galaxies, so you have to weight
I
it.
understand. So the way we treat this analysis is to only consider the mean.
Yeah, I can see that.
Yes.
But then it gives me concern about
I
the
understand.
universality of B of k.
Oh, this is something we have worried about, and it's what delayed this analysis quite a bit, is because we also had this concern. This is by no means a realistic description of a single galaxy sample. So my simplistic way of thinking of this is, let's just say my galaxy samples are divided into their halo masses. They're halos with 2 different mass bins. I have 2 different values of B, but also of B01 and also of this smoothing scale.
Right.
And what I really want to do is to average over all of them with their abundances properly
But that could
accounted
also
for.
impact
And
the
I
smear.
understand that then gas physics, etc., will play a role here. What we found is that this is a reasonable, simplistic description of the mean behavior. If you choose not to overinterpret the values of B1 and BV that you get from here, right? So if I now try to say I got B1 of 1 and BV of something, and this means that I have red galaxies living in a hot gas or something, I think this is not going to work because this model is not that realistic. I am, and Ravi is also very interested in building better models of this.
So let me describe something we did a couple of years ago, and I won't take very much time. But okay, I'll describe it to you offline.
Then Glenn, and then we go.
Okay, I'll be brief. This is really nice. I think it illustrates, in particular from this question, the philosophical difference we had with Ravi over this, which is that if you don't do this, you still get really
reasonable constraints.
You get quite good constraints that are model agnostic, and you don't end up learning about all this interesting physics. Now it would be interesting to compare, and you're saying now I can learn about it, but we're hearing about exactly the complications that worried Stefano and I, Stefano in particular.
Fine. I mean, what you're saying is that because this is so uncertain, you should live with the fact that probably the only thing you can get at is the linear point or something similar. And the coefficients that you're talking about, most likely, because those coefficients, if I translate to my language, will get, in my language, they will be contaminated by the effects of sigma v, as well as the effects of scale-dependent bias and mode coupling.
But collectively, we did a very elaborate analysis of the errors.
I understand, absolutely.
And
yes.
And there's a Euclid paper making its way through the Euclid refereeing process, hopefully towards the end of it, and it comes out with some limits, some forecasts that I can't tell you. Right? But they're very similar to what Ravi, Stefano, and I found back when we did.
I think that's fair enough. I think philosophically we disagree on this point. My approach is to say that there is useful information here, and I think it can be extracted in an interesting and robust manner.
And I don't disagree, but I'm not sure the reduced error bars on the linear point, which is so on the cosmological scale.
You see, now they probably won't be reduced as much as you might have thought, because whenever you do that comparison, you fix f sigma v.
No, that was
exactly, and then you get a reduced error bar. Here, I think I would probably be, my errors will probably be comparable to yours, but I have constraints which you don't have. Yeah, so that's the new thing.
Right, and but because of the complications that Dick has just raised.
Well, can I say why
Yeah.
we want to do this and why we have done it? But we did it with peak patches, and it was absolutely brilliantly throughout this whole regime with the different kinds of galaxies present. But the most important thing is that you can constrain in this region, which is relatively clean, primordial intermittent as well as the running bias that
I see.
that is the usual one that people try and get. And so it can actually be a really good diagnostic tool for the breaking of the essentially Gaussian assumptions at the beginning. And I'm not sure that what you're describing can do that.
We were making no attempt to do
No, well, I know. I'm just saying that
No, but he wants
what
to do
you
it,
want
so-
to do is to use it as a tool.
for that. Yeah.
Well, for many things, but that in particular.
Let's discuss this. This is very interesting.
I think it's a good segment to coffee break now.
Yeah. Sorry, I cut you off. Yeah.
Basis functions that are learned, they're like